What I'd like to do now is show you how to do a calculation of a Kb value and a pKb value given the initial concentration and the pH of an equilibrium solution. Right, so what we're going to be working with is a CH3 and H2. Now, because we're dealing with Kb, we know that what's going to form is OH minus. That is because B is for base, and that's what we're going to be after. We're after an expression involving OH minus, not H plus. Now, Ka would have been H plus, but Kb is OH minus. If we're going to get OH minus, then that's going to necessitate using water as part of our equation. Now, you'll recall in the case of Ka, you could get away with using water or not using water. But here with the bases, because we're forming OH minus and the OH minus is clearly coming from the water, we must include water in our equation. Now we have to figure out what else we're getting with it. And we've got CH3 and H2. We're missing a hydrogen off the oxygen now. So that hydrogen is now with this part of the compound. So this will be CH3 and H3. If you look at it, it's just what's left over. We've got OH over here, and this will be the CH3 and H2 plus the hydrogen we took off this. Additionally though, it'll also be positively charged. And the reason for that is because we need electrical neutrality in our equation. We've got 0 over here, we've got negative here, which means this whole thing must be positive. Now this makes sense because this would have had to have taken an H plus off the water, and that's what makes it a base, is it takes an H plus, and when it takes an H plus it becomes this compound. Alright, now we can go ahead and do our assigning. We've got initial concentrations, we've got equilibrium concentrations. Initial concentration is 0.30, that's 0, and that's 0. Equilibrium, 0.30 minus Z, and this will be Z, and this will be Z. Now this is the same as what we dealt with the Ka. When this reacts with one water, we're going to get one of these and one of these. And what that also will mean is this will go down by 1, but these will go up by 1, and this will go up by 1. So the amount of CH3 and H2 is going to go down by an amount Z, but these two will go up by the same amount. Got to remember, if we're starting at 0.30, it can only go down. And since this is at 0, it can only go up. Alright, what we need to do now is find a link here so we can get the concentration of OH minus. If we get the concentration of OH minus, we can get Z. Alright, so first of all we have a pH. And the pH is 9.97. Now we know there's a link between pH and pOH, and that is that pH plus pOH is equal to 14. So pOH will equal 14 minus 9.97, and that's going to be 4.03. Alright, so that's our value of pOH. Now here's what we know. We know that pOH equals the negative log of the OH minus concentration. From there we can find the concentration of OH minus will be 10 to the negative pOH, which would be 10 to the negative 4.03, which equals 9.33 times 10 to the negative 5 molar. Right, so that's our concentration of OH minus, which also happens to equal Z. The reason for that is because at equilibrium, Z is the concentration of OH minus. Get rid of all of this. Let's now look at how we calculate the Kb expression. Now Kb is equal to the reactants over, products over the reactants, so the concentration of OH minus times CH3 NH3 plus over the concentration of CH3 NH2. Now we can just plug those values in. It'll be Z squared over 0.30 minus Z. Let's make that Z squared. Alright, so now we can plug in our value of Z, which we calculated to be 9.33 times 10 to the negative 5. And when we plug that in and do our calculation, we're going to come out with a value of 2.9 times 10 to the negative 8. So that's the value of Kb. The value of pKb then will be the negative log of that, and that's going to be 7.5. So in your calculator you would take the log of 2.9 times 10 to the negative 8 and then take the negative of that number, and that should give you that.